Hi everybody, so we had an introduction to KSP. Now we're going to look at how the solubility of salts is affected by either common ions like we've seen with buffers or with acids and bases. So let's take SRF2 as an example. It has a KSP of 7.9 times 10 to the negative 10th. And first we're going to calculate its solubility in water. So this is the normal solubility. If we made a saturated solution of SRF2, what would be the solubility? So we're going to start with the dissociation equation. So SRF2 solid will dissociate partially into SR2 plus and 2F minus. We'll write our KSP expression. Concentration of the SR2 plus ion times the concentration of the F minus ion squared. And let's say that the concentration of the SRF2 as a saturated solution is equal to X. Then this is going to be X, this is going to be 2X, and then don't forget that's squared. And the KSP is 7.9 times 10 to the negative 10th. Now just to point out here, a lot of people are confused by this 2 and then the squared. So the squared comes from the KSP expression. If we had values for the SR2 plus and the F minus, we would just plug them in here. It wouldn't be double or anything. It would just be whatever the F minus concentration is. It's just that we don't have the F minus concentration, and so we're relating it to something else, which is half of that one. So that's why we double it there. But again, if you were given the F minus concentration, you would just plug it in there without the 2. And then again, the square comes from the KSP expression. Anyway, if we solve for this, X is equal to 5.82 times 10 to the negative 4th molar. And so if I'm dissolving SRF2 in water, I could dissolve 0.00006 moles, basically, in a liter. All right, now, what if we put this in a solution of strontium nitrate? So instead of just dissolving it in pure water, I'm going to dissolve my SRF2 in strontium nitrate, 10th molar strontium nitrate. So what would happen then? Well, let's start with our dissociation equation. So I'm going to write the dissociation equation of the SRNO3 first. Sorry, that's one arrow there, because that's a soluble salt. So SR2 plus 2NO3 minus. I know that this is 10th molar, and since this goes to completion, this is also 10th molar. This would be 2/10 molar, right? Okay, and then I'm going to write now my dissociation equation for my SRF2 solid. That dissociates into SR2 plus and then 2F minus. Now, you could do this in two ways. You could do an ice chart. That would be more correct, but honestly, you can just kind of plug it in. Let's do the ice chart so that we do it more correctly. And by the way, this is no longer on the AP exam, this calculation. It could ask you what would happen to the solubility of the SRF2, so you would do it qualitatively, but they wouldn't ask you to do this quantitatively. So this is a solid, I don't care about it. Initially, this is 10th molar from the SRNO3 This was 10th molar there. And initially, I don't have any of my fluoride. And then some of the SRF2 is going to dissociate, and so I'm going to gain X here, and I'm going to gain 2X here. So this is 0.1 plus X, and this is 2X. I'm going to write my KSB expression. My KSB expression is going to be the concentration of the SR2 plus times the concentration of the F minus squared. My KSB is 7.9 times 10 to the negative 10th is equal to, my SR2 plus concentration is 0.1 plus X, and then this concentration is 2X, and then again, don't forget to square that. If you solve for this, you get that so X here, which is how much dissolved of the SRF2, is going to be 4.44 times 10 to the negative fifth molar. So let's see what happened. If this was the concentration of the SRNO3, or sorry, the SRF2, comparing that to my previous calculation, my solubility decreased. This number is much lower than that number, a little bit over 10 times lower. So why is that? Well, if I look at this equilibrium here and I have more SR2 plus, it's going to shift to the left to make more solid and less of the ions. And so if I have a common ion, whether it's SR2 plus or the F minus, it's going to be less soluble because it's going to shift to the left, again, to make more solid and less of the ions. And so therefore it's going to be less soluble. So now, let's look at what happens if I dissolve my SRF2 into a solution that's 0.2 molar of NaF. Well, there's F minus there, so that's going to be a common ion. And so I'd expect it to be lower than my solubility in pure water. But would I expect it to be lower than this? Or between those two numbers? Well, first of all, this is 0.2 molar. Second, for every one of these, there's two of these, so the effect of the F minus as being there is more than the effect of the SR2 plus. So I'd expect it to be lower, but even lower than this. Let's see what we get. So I'll start with my dissociation equations. NaF dissociates fully into Na plus and F minus. This is 0.2 molar, so this is 0.2 molar, and this is also 0.2 molar. Then I'll write the dissociation for my salt. SRF2 solid dissociates into SR2 plus 2F minus. I'm going to start with an ice chart. Don't care about my solid. This starts out as 0, but the F minus from this is 0.2 molar. X amount of the SRF2 solid is going to dissociate, and so I'm going to form X amount of SR2 plus and 2X amount of the F minus. So this is X, and this is 0.2 plus 2X. My KSB is 7.9 times 10 to the negative 10th. That is equal to the SR2 plus concentration times the F minus concentration squared. If you solve for X, that ends up being 1.98 times 10 to the negative 8th molar. That decreased by a lot. Let's look at the two values here, or the three values I should say. So this was in water, decreased a little bit in 10th molar strontium nitrate, decreased a lot, more than 10,000 times less. When I put it in NaF, this is 0.2 molar, but because the fluoride is has a double effect, actually square the effect, that's why it goes down way, way more. All right, so that's adding common ions to your salts. It will decrease their solubilities. What if I change the pH of my solution, what would happen to the solubility of my salt? Again, the calculations for these are no longer on the AP exam. I'm not going to ask you to do them, but you just need to do them qualitatively, not quantitatively. So the first one here asks you which would be more soluble in an acidic solution, AgCl or Ag3PO4. This is a poorly worded question. What they're asking is which one would its solubility increase if it's in an acidic solution? So what we would do is we would write out our dissociation equations as always. So I'm going to go ahead and do that. So AgCl dissociates into Ag plus and Cl minus. Ag3PO4 dissociates into 3 Ag pluses and then PO4 3 minus. All right, well, let's see what would happen if we dissolve these in an acidic solution instead of just pure water. Well, an acidic solution means that I'm adding H pluses. I have extra H pluses added. So, first thing you check, are there any common ions? Well, let's start with the AgCl. No common ions, there's no H plus here. Next, you check if anything would react with that H plus. Well, Ag plus and H plus would not react together. Usually, you never have two positive ions reacting together. Let's see, how about H plus and Cl minus? Would those react together? The answer is no, because you can't form HCl. That's a strong acid. It's going to dissociate right back. And so if I dissolve this in an acid or if I dissolve it in water, it doesn't matter. There is no effect. Dissolving this in an acid does not have any effect on the solubility of it. Let's look at the Ag3PO4. So first we check, are there any common ions? Nope, there's no common ion there. How about the reaction? We said, well, Ag plus and H plus cannot react together. They're both positives. How about H plus with PO4 3 minus? Can that react? Yes, it can. So if I take H plus, let me rewrite that. H plus plus PO4 3 minus, that would be an equilibrium. And you would form HPO4 2 minus. Could argue even that could also, add an H plus to it and form H2PO4 minus, and so on. So what does that do? Well, if the H plus is going to react with a PO4 3 minus, that means it's going to use up the PO4 3 minuses to form this. So I'm removing some of the PO4 3 minuses. What would that do? That would shift the equilibrium to the right to make it more soluble. So this would be more soluble in acidic solution than in a neutral solution. Okay, so again, this question is not a very good question. It's not worded very well, I should say. The question should say, which one would dissolve more in an acidic solution rather than a neutral solution? And the answer would be the Ag3PO4. We're not saying that Ag3PO4 is more soluble. We don't know that because we don't have the KSPs. All right, let's look at the next one. Same thing, it's poorly worded, and so it's really asking us which one would dissolve more if it was in a basic solution. So, as always, you start out with writing your dissociation equations. So KBrO3 solid would dissociate into K plus and BrO3 minus. MgOH2 would dissociate to give off Mg2 plus and 2OH minus. So let's look at this one. When I add this to a basic solution, I have plenty of hydroxide swimming around. So let's look for common ions. OH minus, no common ions for this one. Let's see if it would react with anything. K plus and OH minus, there will be no reaction there because I cannot form KOH. That's a strong base, so it's going to dissociate right back. And then I can't react two negative ions together. So if I dissolve this in a basic solution, there will be no effect on the solubility. It would dissolve the same amount in a basic solution as it would in a neutral solution. Let's look at the MgOH2. Oh, looks like there is a common ion here. And so if I try to dissolve this when there's extra OH minuses, what would it do? It's going to shift the equilibrium to the left, and so it's going to dissolve less. So this would be less soluble in a basic solution compared to a neutral solution. All right, let's look at the last one here. It says you would like to dissolve a significant amount of BaOH2. What type of solution would you add? And you want to write the appropriate reactions. So what are our choices? We could either dissolve it in a neutral solution, a basic solution, or an acidic solution. What would be best? Well, let's start with the dissociation equation. So we have OH2 dissociating into Ba2 plus and 2 OH minuses. All right, well, let's look at if we add an acid. So in an acidic solution, that means I have H pluses floating around. So if I have H pluses floating around, well, let's check. Do I have any common ions? No common ions. Would I have any reaction? Well, H plus and Ba2 plus would not have any reaction. How about H plus and OH minus? Yep, there would be a reaction there. My H plus and my OH minus would react to form water. So what does that mean? That means that I'm removing the OH minuses in an acidic solution, and so which way would it shift? It would shift to the right to dissolve more. So that tells us that it is more soluble in an acid. How about if I have a basic solution? That means I have a bunch of hydroxide ions. Well, let's look. So hydroxide here, how about my ions? Oop, I have a common ion there. So if I have a bunch of hydroxide ions, it would shift to the left to make it more of the solid, make it less soluble. And so this is less soluble in a base because of the common ion effect. And so to answer this question, I would rather dissolve it in an acidic solution. That would give me the best results. It would make it the most soluble.